Hello, I'm Seema and welcome to part 14 of the chapter Haloalkanes and Haloarenes. Let us now start talking about the reactions of haloalkanes. There are three categories of reactions of haloalkanes that we will be studying. The first is nucleophilic substitution reaction, the second is elimination reaction, and the third is reaction with metals. In this video, I'm going to start doing the first category, that is nucleophilic substitution reactions. Elimination and reaction with metals we will be doing in the consecutive videos, and right now I'm going to introduce the nucleophilic reactions to you. Nucleophilic substitution reaction. You know what substitution is. Substitution is when one substance takes the place of another. Like if you have an ionic compound, one of the atoms takes the place, one of the ions takes the place of the corresponding ion in the molecule. Such a reaction is known as a substitution reaction. You've done substitution reactions when you did redox reactions in your grade 11. So you understand what substitution is. If a teacher does not come on a certain day, then you have another teacher who substitutes for that teacher. So you understand the meaning of the word substitution. Substitution is where one thing takes the place of another thing. Now you do understand substitution. What about nucleophile? In chemistry, whenever you have to relate something to you're talking of negative charge, we usually think in terms of atoms. In an atom, the electrons are negatively charged. So whenever we are talking of something negative, we tend to relate it to the electrons. And if there is something positive, we know in an atom, the nucleus is positive in charge. So anything when we are talking of it to be positive, we say it is like the nucleus, right? So the nucleus is positive. So when we talk of nucleus and electrons, we are kind of indicating towards the charges. The nucleus would be positive and the electrons would be negative. So when we spoke of electrophile or electrophilic reaction, electro we meant was negatively charged electrons, and philic or anything being philic means being attracted towards it. So electrophilic is something that loves electrons, and nucleophilic would be something that loves the nucleus. So anything that loves electrons means that it is attracted towards negative charge. And when we say a nucleophile, something, nucleus is positive, and phile, it loves the positive charge. So something that is attracted towards positive charge would be a nucleophile. So now what would be attracted towards positive charge? Anything that is negative would be attracted towards positive charge. Similarly, therefore, a nucleophile is a negative species. A species that is negatively charged. A negatively charged ion would be attracted to the nucleus. On the other hand, what would an electrophile be? An electrophile would be something that is attracted to electrons which are negative. So an electrophile should be a positively charged species. So from this we understand what would a nucleophilic substitution reaction be. A nucleophilic means it would be a negatively charged species which would replace the negative part in the haloalkane. What is the negative part in the haloalkane? The halogen atom is the negative part. So a nucleophilic substitution reaction would be one which is attracted towards, which itself is negative. So it is attracted towards the positive part of the haloalkane. What will be the positive part? Anything other than the halogen would be the positive part. So it is attracted to the positive part, but it replaces or substitutes the halogen, right? So what is happening? In a nucleophilic substitution reaction, a nucleophile which is negatively charged species, it attacks the positive part of a haloalkane. What is the positive part in a haloalkane? There is a halogen which is negatively charged, which pulls since it has more electronegativity, it pulls the shared pair of electrons towards itself, thereby acquiring a partial negative charge. And the carbon, on the other hand, in the bond pair if the electrons are pushed towards the halogen, the carbon which is attached to it, it becomes a little deficient in electrons, and therefore it becomes positively charged. So this is the positively charged center which the nucleophile is being attracted to. So the nucleophile is attracted to the positively charged center, or the carbon, which is attached to the halogen in a haloalkane. This carbon is sp3 hybridized. Right? This carbon is sp3 hybridized. It is attached to the halogen, and therefore it has a partial positive charge on it. A nucleophile is attracted towards the nucleus, or the positive charge. So any species that is negative in charge, or any species which has electrons to give. It is not necessary that the species be negatively charged. If the species has electrons which can be given for reaction, such a species would also act as a nucleophile. And what is such a species that would have a lone pair of electrons on it? That would have a pair of electrons? A species that has a lone pair of electrons on it. For example, ammonia. In ammonia, nitrogen has a lone pair of electrons. So any species that has a lone pair of electrons which can be provided and thereby lead to a substitution of the negative part would also act as a nucleophile. So we understood what a nucleophile is and what happens in a nucleophilic substitution reaction. So let us see this schematic equation that is given. A nucleophile, which is negatively charged, attacks the haloalkane. The halogen is partially negatively charged, and the sp3 hybridized carbon which is attached to the halogen is partially positively charged, and it is this carbon which is attacked by the nucleophile. We'll be doing the mechanism of the reaction in the next video. Right now you just have to understand what a nucleophilic reaction is. And this leads to the attachment of the nucleophile to this, and since it is substituting the halogen has to move away. The halogen leaves and the nucleophile takes the place of the halogen and results in the bond between carbon and the nucleophile while the halogen is given out. Therefore, what is happening in this reaction is that the halogen is leaving. The halogen is leaving the molecule, therefore the halogen is known as the leaving group. Right? Just a little terminology that you should be aware of. The halogen is the leaving group and the nucleophile is the attacking regent. It is attacking, and the substrate on which it will come and attack is the haloalkane, while the halogen in the haloalkane is the leaving group, the group that will leave. So if you look at the reaction, what would it be like? You have a haloalkane. R stands for an alkyl group and X is any halogen. It combines with the nucleophile and it results in the combination. The nucleophile takes the place of the halogen, thus substituting it. So you get RNU, that is nucleophile, and the halogen leaves with those electrons. So the negative charge goes with the halogens. So let us now discuss a few examples of such nucleophilic substitution reactions that are shown by haloalkanes. In each one of these reactions, I've put the haloalkane as the alkyl group R and X as any halogen. And the attacking regent is written next to it and the products are given. So these are all kind of general reactions, but these are the kind of reactions that are shown by haloalkanes. So let us discuss them one by one. If you have the haloalkane and it reacts with sodium hydroxide or potassium hydroxide, it results in the formation of an alcohol. In this sodium hydroxide, which part would be the nucleophile? The nucleophile would be that part which is negative. We know that in sodium hydroxide, which is an ionic compound, sodium would be positive and OH would be negative. So here, the nucleophile is going to be OH, right? So OH attacks the R part, the carbon which is attached to the halogen, and it results in the substitution. Therefore, you get X leaves as the leaving group and you get ROH, and the positive part here combines with the negative halogen and results in the formation of NaX. It could be NaCl, it could be NaBr, whatever. In the next reaction, you again have a haloalkane and you make it react with water. Reaction with water and breaking of a molecule with the help of water is known as hydrolysis. Lysis means breaking and hydro means water. So breaking of a molecule due to water is known as hydrolysis, just as breaking of a molecule with the help of electricity is known as electrolysis. Similarly, hydrolysis is breaking a molecule with the help of water. So it leads to hydrolysis, and as a result of hydrolysis also, the product that you get is an alcohol. In water, you have H positive and OH negative if we try to find the ions in it. Although it is non-polar, yet these are the charges that would develop in the molecule. So Rx, when it reacts with H positive and OH negative, the OH negative combines and it substitutes the X and results in the formation of ROH, and the X combines with the hydrogen which is left to form HX. In the third reaction, you again have a haloalkane and it reacts with NaOR-. What is NaOR-? It is sodium alkoxide. This sodium alkoxide, when it reacts, now sodium is positive and OR dash, R, when I put the dash, it means the dash, the R, the alkyl group here and the alkyl group here may or may not be the same. That is why we put an R dash to specify that this is this alkyl group, and the alkyl group R is the one that we took with the haloalkane. So when Rx combines with NaOR dash, OR dash becomes the nucleophile and that substitutes the X. So you get ROR plus NaX. This is an ether, right? ROR dash is an ether. So you'll get an ether here. Then you have Rx. It combines with NaI, sodium iodide. And Rx is the halogen. We've done this, the halogen exchange method that we had done. We did this reaction when we said how do we prepare iodides by halogen exchange method. So we take sodium iodide and the haloalkane, and iodine usually replaces chlorine or bromine in such reactions. So you would get the alkyl iodide and NaX. This is also a nucleophilic substitution reaction. The fifth example is where you take the haloalkane and make it react with ammonia. Reaction with ammonia is important in the sense that it is a very interesting reaction. It does not take place in just one step. The ammonia, it takes place in more steps. If you continue the reaction, you get both the primary, the secondary and the tertiary amines can be obtained by this. And this method is known as the Hofmann's ammonolysis method. What do we do in this? You take the haloalkane, you make it react with ammonia. NH2, one of the hydrogens will be H and NH2. NH2 becomes the nucleophile. Now NH2 substitutes the halogen, and the hydrogen which is left, it combines with the halogen to form HX, and RNH2 is a primary amine that you get. Now if you take this primary amine and you further react it with a haloalkane, now take a look. You have RNH2, but in the next step we just make this as R-NH2 so that you can differentiate between these two R's. And assuming that this R is now R- in the second step, and we further react it with the haloalkane, what do we get? Another hydrogen of the NH2 group is replaced here, or another hydrogen combines with the halogen and it leads to the nucleophilic substitution, and you get RNHR-. This hydrogen combines with the halogen and this group joins it as the nucleophile, and you get HX. So this gives you a secondary amine. Did you understand what happened here? One of the hydrogens from RNH2, R-NH2, one of the hydrogens, R-N, becomes the negative part and NH becomes the negative part, and one hydrogen combines with X to form HX, and this R-NH, it combines with R to form RNHR-, which is a secondary amine. What is a secondary amine? A secondary amine is one in which two of the hydrogens of the amine of the ammonia are substituted by alkyl groups. So you get a secondary amine. If you further react this, the product that you get here, R dash, now we'll convert the R into R dash and R dash into R double dash, so that again it appears to be different from the alkyl halide that we are still using again. So Rx reacts with R dash, R double dash, NH, which we got as a product here. And when we carry out this reaction, this hydrogen also will be used to form HX, and R dash, R double dash, N, that will become the nucleophile, and you will get a tertiary amine this time. So the third hydrogen is also replaced, or rather the third hydrogen is also combines with the halogen, and this part acts as the nucleophile, and you get a tertiary amine. That is R, N, R dash, and R double dash. So to nitrogen, all the three hydrogens of the ammonia have been replaced by alkyl groups, therefore this is a tertiary amine. So the Hofmann's ammonolysis, this is a very interesting reaction because it takes place in 3 steps, and it gives you all 3 amines. It gives you the primary, secondary, and tertiary amine. In the next reaction, this again is a very interesting reaction. When you have a haloalkane reacting with potassium cyanide, it gives you RCN, that is, the K is positive, Cn is negative, so Cn negative is the nucleophile. This nucleophile substitutes the halogen, so you get RCN and KX will be obtained. Now this is RCN would be alkyl cyanide. So you get a cyanide or a nitrile. It is also known as a nitrile. Now what is interesting about this reaction is the cyano group. The cyano group is a nucleophile which is known as an ambident nucleophile. You know, a person who uses both hands and he can write equally well with the right hand as well as with the left hand. He does his work with right hand as well. We always have a strong hand and a weak hand. So sometimes we say I'm right-handed, I'm left-handed. There's a person who uses both hands equally. What do we call that person? Ambidextrous. A person who can use both hands equally efficiently. Similarly, this is a nucleophile which is known as an ambident nucleophile. What is dent? Dent is teeth, right? So when chemicals react, it is as if they have the teeth of keys. Keys, if you see a lock and a key, the key has teeth in it, and the indentations inside the lock are the same which match the key. It is as if this is the key and this is the lock. The holes inside the lock would be exactly of the shape that the key, the indentations or the teeth of the key will exactly fix into it, only then the lock opens or closes. So it is somewhat like that. When we say it is ambident, it says that this nucleophile can act as a nucleophile at two positions. At carbon also, it can go and attach to the alkyl group. It can also attach to the alkyl group or acts as a nucleophile at nitrogen also. It can attach itself from nitrogen also. When do we see this? We see this in another reaction where you have the haloalkane and it reacts with AgCN. If we do not take potassium cyanide, instead we take silver cyanide, we find that the product is not the cyanide that is formed, the product is isocyanide. What is isocyanide? Isocyanide means it is the nitrogen which attaches itself to the carbon and not the carbon. So the teeth, it is such a nucleophile that has teeth on this side and teeth on this side also. So either this one can go and fit into the, it can go and attach into the key, into the lock on this side, or this other key can also go and attach itself. It can attach itself on either side. So it is an ambident nucleophile. And why does this behave as an ambident nucleophile? Why do we get a cyanide in the case of potassium, and why do we get isocyanide when we take silver cyanide? The reason is that potassium cyanide is an ionic compound. So potassium gives you K positive and Cn gives you Cn negative. You get proper ions. And the bonding between, the covalent bond between carbon and carbon is quite stable. That is why carbon has that property of catenation. That is why carbon forms so many compounds. That is why we have organic chemistry basically, because of the property of catenation of carbon atoms. That the carbon-carbon bond is a very stable bond. So the carbon-carbon bond is stable and the compound is ionic in nature, therefore it becomes very easy. The ion, the nucleophile, it goes and attaches itself. It has the option. It is ambident. It has got teeth on both sides, but the carbon, the side of the carbon is what will go and join, because it will result in the formation of a more stable bond. But then, why is that choice not made available in the case of AgCN? Why does nitrogen attach itself to the carbon? Here also carbon-carbon would have formed a more stable bond, but then why did nitrogen go and attach itself? The reason there is that AgCN is a covalent compound. Since it is covalent, in an ionic compound, it is very easy for the ions to separate. If you dissolve the ions, if you take common salt and you dissolve it in water, it separates out into its ions, that is Na positive and Cl negative, and they move apart. So it is easy to move the ions away. But when there is a covalent bond, silver and carbon, they are attached by a covalent bond. The nitrogen which is attached to the carbon, it has got a lone pair of electrons. It is this lone pair of electrons which forms the dent, the teeth. What were the teeth? Either a negative charge, that is electrons themselves, or a pair of electrons in the form of lone pair of electrons would also act as the teeth. So the second set of teeth that this nucleophile has is the lone pair of electrons on nitrogen. So the silver and carbon have not yet separated, they are still holding on to each other, and the nitrogen, which has the lone pair of electrons, uses that opportunity and acts as the nucleophile and comes and attacks the carbon attached to the halogen, thus acting as a nucleophile from the nitrogen side. And once it attaches itself, after that the silver ion, it has to move away, and that combines with the halogen, resulting in the formation of the silver halide. So cyanide group or the cyano group is an ambident nucleophile. Then comes the next example. The haloalkane, it reacts with potassium nitrite, KNO2, and it results in the formation of the alkyl nitrite. Again, this is a nucleophile. It is ionic. It is an ionic compound. K positive and NO2 negative will be formed. So the NO2 negative will come and attach itself to the alkyl group, and the potassium halide, the positive part, will combine with the halogen and result in the formation of potassium halide. And just like the cyano group, the nitrite group is also an ambident nucleophile. So what happens when you have an ambident nucleophile like the nitrite group? If you have Rx and you combine it with, again, the same situation, AgONO, that is silver nitrite. When you combine it with silver nitrite, the attachment does not take place at oxygen, it takes place at nitrogen. And what you get is nitroalkane. Instead of getting alkyl nitrite, you get nitroalkane. Again, it is the lone pair of electrons present on nitrogen which will do it. The reason is the same, that this is a covalent compound, that's an ionic compound, and the same reason works here also. So we find that nitro group or the nitrite is also an ambident nucleophile. If you make the alkyl halide react with potassium nitrite, you get the alkyl nitrite, but if you make it react with silver nitrite, you get nitroalkane. Now let us take the next example, that is example 12. In this you have alkyl halide and it reacts with the silver salt of an acid, of a carboxylic acid. So the silver salt of the carboxylic acid would be R-COOAg. So when this reacts, Ag would be positive and RCOO would be negative. So RCOO negative would act as the nucleophile and it would replace the halogen. So you'll get RCOO R dash. And what is that? That's an ester. right? So you get an ester in that case, and it results, the silver combines with the halogen to give you AgX. Equation 13. Here you have the haloalkane, and we carry out the reduction. What is reduction? Reaction with hydrogen is known as reduction. In the presence of lithium aluminium hydride, we carry out the reduction of the haloalkane. Here, one of the hydrogens will take the place of the halogen, and the other hydrogen, one of the hydrogens will take its place, and the halogen will go and combine with the other hydrogen. So you get RH plus HX. Interesting. We had a functional group or a substituent in the haloalkane. This is a method of removing that functional group or the substituent and getting back the hydrocarbon. This is a technique with the help of reduction, with the help of lithium aluminium hydride. You can obtain the hydrocarbon from its haloalkane. 14th reaction would be RX, again, that is haloalkane, combines with R-M positive, a metallic, a hydrocarbon which has been substituted with a metal, in which one of the hydrogens has been substituted with a metal. So in this case also, the metal M positive will combine with X, and R dash would be negatively charged, so R and R dash will combine, and whenever you have two alkyl groups joining together, it results in the formation of an alkane or a hydrocarbon. And the metal will combine with X to form the metallic halide. So these were the different nucleophilic reactions that are shown by haloalkanes. In the next video, we'll discuss the mechanism of these reactions. So if you found, with this I'll just wind up this video. If you found it helpful, give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.